GSM. So what does that stand for? Maybe you're thinking of the Global System for Mobile Communication, GSM, which is a digital mobile network for mobile phones. Perhaps maybe grams per square meter, which is a measurement used to refer to the weight of fabric or paper. But today I want to look at a different GSM. I want to look at gears, screws, and motors. So let's start with our first letter, G, for gears. What is a gear, and what is it used for? A gear is really a cogwheel of a rotating machine part having cut teeth or cogs which mesh with another toothed part to transmit torque or power. In most cases with teeth on one gear being of identical shape and often also with that shape on the other gear. What is it used for? As we've said, it helps transmit torque or power, but it does a lot more than that. It can reverse the direction that a particular shaft is rotating in. It can also be used to increase or decrease the speed of a shaft. And here you're probably more familiar with your car, where changing gears means changing the ability of your car to go faster or slower. So as your car engine turns, there is a limited range in how fast it turns, and you need greater ranges to turn your wheels, and gears provide this in linking your engine to your wheels. If you think of the old wristwatch some of you might have worn in the past, they function through a very intricate series of gears to turn the hour, the minute, and the second hand in perfect harmony and timing. That precision is only made possible by the use of tiny gears all working together. In this particular example that you can see, we have what's called a driver gear with 8 teeth, and with a driven gear having 24 teeth. And so, as you can see, for every one revolution of the driver gear with its 8 teeth, it will only cause the driven gear to rotate by 8 teeth, which for itself means it only rotates a third of a revolution. And so in your wristwatch, for example, for every rotation of the minute hand, you need to have the second hand having to have rotated 60 times. And so there are all sorts of types of gears, spurs, helical, bevel, and so on. And the early examples of gears date from the 4th century BC in China. The earliest gears in Europe were around 50 BC by Hero of Alexandria, and they can be tracked back to the Greek mechanics of the Alexandrian school in the 3rd century BC, and were greatly developed by the Greek Archimedes. And so gears are used extensively in our man-made world, and not just in wristwatches or car engines, but all sorts of machines. Now, when you look at the intricate structure of a machine gear, we would expect it to be an exclusively man-made object and invention. But if that's what you thought, you'd be wrong, because it seems that nature had them first. So let me introduce you to the tiny plant hopper insect, Isis coleoptritus. It is the first living creature known to possess functional gears. It has 2 interlocking gears on its hind legs. And why would it need these? What purpose could they serve? Well, you recall with the mechanical gears we looked at earlier that one of its features is how if 2 interlocking gears are of the same size, so they have the same dimensions and number of teeth, then if you turn one, the other will turn in exactly the same amount, always and precisely. This is a photo through a microscope of this creature's gears. And notice the scale. That is 20 micrometers, 20 millionths of a meter. If you go down to a millimeter, and we can often just try and imagine a small little millimeter on your ruler, that's 20 thousandths of that little millimeter. And so it needs and uses these gears to synchronize its legs when it jumps. With 2 diminutive legs locked into a leap-ready position, the tiny jumper bends its body taut, much like an archer drawing a bow. And at the top of its legs, a minuscule pair of gears engage. Their strange shark fin teeth interlocking cleanly, just like the zip on your dress or on your trousers. And then faster than you can blink, think or see with the naked eye, the entire thing is gone. In 2 milliseconds, it has bulleted skyward, accelerating at nearly 400 Gs. That's a rate that is 20 times what a human body can withstand. And at top speed, this little jumper breaks 13 kilometers per hour. That's quite a feat considering its body size is less than 2.5 centimeters long. And the reason for gearing is coordination. To jump, both of the insect's hind legs must push forward at the exact same time because they both swing laterally, and if one were extended a fraction of a second earlier than the other, it would push the insect off course to the right or to the left instead of jumping straight forward. The gearing is an elegant and brilliant solution. And researchers have used high-speed cameras, and they've shown that this little creature who jumps at speeds as high as 3.61 meters per second, just think of the size of this little creature and how far 3.61 meters is, and it does that in a second. So they've looked at this little creature with high-speed video cameras, and they see it cocking its back legs into a jumping position and then pushing forward, and with each moving within 30 microseconds, they're 30 millionths of a second of each other. The finely toothed gears in their legs allow this to happen. In ISIS, the skeleton is used to solve a complex problem that the brain and nervous system just can't. They just can't work that fast. The gears are located at the top of the insect's hind legs on segments known as trochanteria and include 10 to 12 tapered teeth, each about 80 micrometers wide, or 80 millionths of a meter. In all, the ISIS hoppers studied, the same number of teeth were present on each leg, and the gears locked together neatly. The teeth even have filleted curves at the base, a design incorporated into human-made mechanical gears because it reduces wear and tear over time. To confirm that the gears performed this function, the researchers performed a neat, maybe slightly morbid trick with some dead ISIS. They manually cocked their legs back into a jumping position and then electrically stimulated the main jumping muscle in one leg so that that leg extended. And because it was rotationally locked by the gears, the other non-stimulated leg moved as well, and the dead insect jumped forward. And scientists hope that by mimicking these gears in human technology, we may be able to improve machine function and minimize friction between gears. Modern machines such as 3D printers could easily create gears with these shark fin teeth. And it's hoped that they may perform better in very small machines, as modern machinery often doesn't work at very small scales. And this is because friction doesn't matter so much when you have two big gears next to each other. But when you get very small, friction starts to kill you. And so these little plant hoppers might help to solve that problem. And so I leave this first section with a question. Do you think these gears just evolved on their own? Or does it look like a very intelligent design? Our second letter, S, stands for screws. And very similar to a screw is a bolt. And what is the main purpose of a screw? Well, a screw is a helical threaded fastener capable of being tightened or released by a twisting force or torque to the head. And the most common uses of screws are to hold objects together, and there are many forms for a variety of materials. What is the purpose of bolts and nuts? Well, bolts and nuts are hardware fasteners commonly used in construction, manufacturing, automotive, and various other industries. And they are used to join two or more components together securely. Bolts typically consist of a threaded shaft with a head at one end. Looking into a short history of nuts and bolts have been the absolute unsung heroes of construction and machinery for centuries, dating back to military and agricultural uses in the 10th century. Both nuts and bolts offer the advantage of reusability and adjustability Unlike permanent fastening methods such as welding, nuts and bolts can be disassembled and reused, providing flexibility in design and maintenance. And this makes them ideal for applications where components may need to be replaced or adjusted over time. The Archimedes screw, also known as the Archimedean screw or hydrodynamic screw, is a water screw or Egyptian screw, and it's one of the earliest hydraulic machines named after Greek mathematician Archimedes, who first described it around 234 BC. And as a machine, it was used for lifting water from a low-lying body of water into irrigation ditches. And water is lifted by turning a screw-shaped surface inside a pipe. And as we said, a screw or bolt is a type of fastener, typically made of metal and characterized by a helical ridge known as a male thread, external thread, or just thread wrapped around a cylinder. And some screw threads are designed to mate with a complementary thread known as a female thread or internal thread, often in the form of a nut or an object that has the internal thread formed into it. And again, much like in our case of gears, screws, nuts, and bolts are used extensively in our man-made world. So when we look at the intricate precision of a machined screw or bolt, we would again expect it to be an exclusively man-made object and invention. But again, we would be wrong, because it seems that nature, once again, had them first. So let me introduce to you the little weevil found in New Guinea and neighboring islands called Trigonopterus oblongus. And when scientists used CT scans to study this little weevil, to their surprise, they found that its legs appeared to be screwed into its body. The top segment of each leg, the femur, is attached to a small part called the trochanter. In turn, the trochanter attaches the leg to the insect's body by screwing into a part called the coxa, which is similar to a hip. And inside the coxa and on the outer surface of the trochanter, they found ridges just like those on screws and nuts. The beetles could twist their front legs through 90 degrees and their middle and hind legs through 130 degrees. And the ability to twist its legs in their sockets might be particularly handy for these type of weevils, which live on leaves and twigs and constantly have to splay their legs to find footholds. It looks like the weevils are using the screw and nut mechanism in the opposite way to humans. Humans turn a screw to make it move along its length, but the weevil's muscles pull along the length of its legs to make it turn. So again, we leave this section with a question. Do you think these screws and threads just evolved on their own? Or does it look like a very intelligent design? And in our last letter, M stands for motors. And a motor is a seriously complicated piece of equipment with a lot of different parts, all contributing to its ability to function and work. And how would we describe or define a motor? Well, an electric motor is a machine that converts electrical energy into mechanical energy. Most electric motors operate through the interaction between the motor's magnetic field and electric current in a wire winding to generate force in the form of torque applied on the motor's shaft. And that's the objective at the end of the day, to turn this shaft to have some purpose. So if you have a swimming pool or electrical appliance, you might find something similar to this inside. Now, this is a cutaway of a motor showing some of the internal parts. And here we have extracted out the parts of a motor. And from this we can clearly see three parts I want to just highlight. Firstly, the output shaft, which is what gets turned by the whole motor. Secondly, the rotor. This plays a critical role in generating or interacting with a magnetic field that enables the generation of mechanical motion or power into the shaft. And then thirdly, the stator. And this provides a rotating magnetic field which then interacts with the rotor. So we see all three parts are absolutely vital for the functional performance of our motor. And I guess we can say that the design is very clever, very precise, very finely manufactured, to small tolerances, and there's no room for error. So again, and maybe even more so than in the case of our gears and screws, when we look at the complicated precision of a motor, we would again expect it to be an exclusively man-made object and invention. But again, we'd be wrong, because it seems that nature once again had them first. So let me introduce to you bacteria. That's right, you have loads of it inside of you, on your skin and in your environment. They're just too small to see. Now, have you ever wondered how these little bacteria get around? They don't have legs to crawl or wings to fly. Well, they use this little tail of theirs. Sometimes they have more than one. And this tail is called their flagellum. But how does it work? They can't wag it like a dog. That's not going to help much. The answer is that they have a rotary body part. In fact, they are the only known living organism to have this. And this amazing transmembranous structure spins the whip-like flagellum, which is attached to a stiff hook-like base, which whips the flagellum and causes forces that produce motion. And even more amazing, it is almost exactly like a miniature, and I mean miniature, electric motor. Look at the radius of this motor. 20 nanometers. That's 20 billionths of a meter. It's taking your millimeter and dividing it by 1,000,000. And what we find in this little motor are many of the same core components we find in our mechanical motors. We find a rotor, we find a stator, we find a shaft. But can you think of one problem this little bacteria could potentially have? How does he stop or start his motor? And if you've got any ideas, you might be pondering them at the moment, and I'll give you a clue. How do you control your manual car when you're driving to provide power to your wheels to make it go forward, or remove that power to start the process of slowing down and stopping? And the answer is you have a clutch. And this little guy does so with similar incredible engineering. He has built around his motor a gear and a clutch. He engages or disengages the gear to the rotor using the clutch. And so we have looked at three very different creatures or organisms, each with incredible mechanical functioning parts. And we have to ask ourselves that question again. Do you think these gears, screws with threads, these intricate miniature motors just evolved on their own? Or does it look like a very intelligent design? So let's close with three passages from Scripture to really sum up our thoughts. And the first one comes from Job chapter 12 and verses 7 to 10. And there we read, "But ask the animals, they will teach you, or the birds of the air, and they will tell you, or speak to the earth, and it will teach you, or let the fish of the sea inform you. Which of all these does not know that the hand of the Lord has done this? In his hand is the life of every creature and the breath of all mankind." What is God telling us here? All these years ago, he's saying to us, just observe the animals, the creatures, the bacteria, the little weevil. Look at these creatures and look at the intricate design that I've placed into these creatures. And which of these does not know that the hand of the Lord has done it? When you look at it, you can only come to the conclusion that there had to be an intelligent designer, that is God himself, who was behind the creation of all these marvelous little creatures. In Psalm 104, verse 24, "How many are your works, O Lord? In wisdom you made them all. The earth is full of your creatures." And we've just looked at three of them here. And then finally, Psalm 14 and verse 1. "The fool says in his heart, there is no God. If we look at these little creatures and the incredible things that they have to enable them to function, we can come to no other conclusion than that there is a creator behind them. Otherwise, we are just a fool in our hearts.